Expression for torque in terms of moment of inertia. Consider a rigid body of mass m is rotating with a constant angular acceleration alpha about its axis, which is perpendicular to this plane of paper or plane of this rigid body. Let us consider that this object to be consisting of n particles of masses, say m1, m2, m3 and so on up to the mnth at respective perpendicular distance, say r1, r2, r3 and so on rnth from this axis of rotation. That means the mass particle m1 is at a perpendicular distance r1, mass particle m2 is situated at a distance r perpendicular distance r2, mass m3 is situated at a perpendicular distance r3 and so on. The mass particle mnth is situated at a distance rn from the axis of rotation. As the object rotates, all these particles perform a circular motion with the same angular acceleration but different linear acceleration, and hence we can write down that A1 is equal to R1 alpha, A2 is equal to R2 alpha, A3 is equal to R3 alpha and so on, Anth is equal to Rn alpha. Here it is found that the force is also acting on this each mass particle. We can say that the force F1 is acting on a mass particle M1, force F2 is acting on a mass particle M2, force F3 is acting on a mass particle M3 and so on. The force Fn is acting on a mass particle Mn. Let us calculate the force experienced by each mass particle of this rigid body. Let us calculate the force experienced by a particle m1, and that is F1 is equal to m1 a1. A1 is a linear acceleration acting on mass m1, and we can write down the value of a1 in terms of angular acceleration, and we can get the value of F1 as a m1 r1 alpha. These forces, that is the force acting on the mass F1, F2, F3 and so that up to the Fn, are tangential at their respective perpendicular distances, say R1, R2, R3 and so that up to the Rn from their axis about which this rigid body is rotating. Thus, the torque experienced by a mass particle m1 can be written in magnitude as torque 1 is equal to F1 into R1. This is a formula for the torque, that is a force into perpendicular distance. The force acting on a mass particle m1, it is given by m1 r1 alpha. So it is written over here, and then multiply with the r1, and then we get the value of torque 1 is equal to m1 r1 square alpha. Similarly, we can calculate the torque acting or the experience by a particle m2 as torque 2 is equal to F2 into R2. Substitute the value of F2. We can write here m2 into A2 into R2. Substitute the value of this A2 in terms of angular acceleration. So we get the value of torque 2 as a m2 r2 square alpha. Similarly, we can calculate the torque acting on a nth mass particle, that is equal to torque n, that can be written as Fn into Rn, and that value comes to be Mn Rn square alpha. If the rotation is restricted to a single plane, the direction of all these torque T, tau 1, tau 2, tau 3 to tau n are same and along the axis. The magnitude of the resultant torque is given by torque of a rigid body is equal to tau 1 plus tau 2 plus tau 3 plus dash 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 plus tau n. So we'll substitute the value of the each torque in this equation and we'll take the common factor alpha out of the bracket, and hence we can get the equation as torque is equal to into the bracket m1 r1 square plus m2 r2 square plus m3 r3 square plus dash 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 plus mn rn square, close the bracket, into the common factor alpha. Now we know that this summation is nothing but the inertia of the body, and by definition we can just write down the inertia or the moment of inertia of a rigid body is equal to summation of mi ri square, where I stands from 1 to n. Just substitute the value of I in this above equation, and hence we can write down the torque is nothing but the summation of mi ri square, where I stands from 1 to n into alpha, and hence we can write down the torque value is equal to I into alpha. So this is the expression of the torque in terms of moment of inertia. Now this relation torque is equal to I alpha is analogous to the force is equal to m into a for the translation motion if the moment of inertia I replaces mass, and which is its typical significance.